Tonight, we're going to explore one of the most audacious missions humanity has ever attempted. A spacecraft built to do something that for centuries was considered impossible. To fly into the atmosphere of a star, not orbit at a safe distance, not photograph from afar. Actually plunge into the outer layers of the sun itself, into temperatures that would vaporize any ordinary material in a fraction of a second, and survive. The Parker Solar Probe launched in August 2018, carrying instruments designed to do something no spacecraft had ever done before, and what it found there shattered every model scientists had built over the last 100 years. The corona was hotter than physics said it should be, by a factor that no theory could explain. The solar wind didn't flow the way every textbook had described for 60 years. There were structures in the sun's atmosphere that weren't supposed to exist. Magnetic fields that bent back on themselves in violent S-shaped kinks no one had predicted. A region near the sun where dust simply vanished. An empty zone that astronomers had argued about for decades and finally confirmed existed. 7 major discoveries that proved we had been profoundly wrong about the star our entire civilization depends on for survival. By the end of tonight, you're going to understand how a spacecraft the size of a small car, traveling faster than any human-made object in history, survived a journey into the atmosphere of the sun and brought back data that is currently rewriting astrophysics textbooks across the world. Before we begin, if you love exploring the deepest mysteries of our solar system as much as we do, take a second to like the video or subscribe. It's a small action, but it helps this channel reach more curious minds like yours. Now, let's begin. The story starts not in 2018, but in 1958. A young physicist named Eugene Parker, working at the University of Chicago, published a paper that almost ended his career. He proposed that the sun was constantly losing mass through a high-speed stream of charged particles flowing outward in every direction. He called it the solar wind. The scientific establishment laughed. Reviewers tried to reject his paper. One reviewer wrote that Parker should go to the library and learn some physics before publishing again. The idea seemed absurd. Stars were supposed to hold themselves together with gravity. The notion that the sun was bleeding particles into space at hundreds of miles per second sounded like science fiction. But Parker was right. Within 4 years, the Mariner 2 spacecraft confirmed his prediction. The solar wind was real. It flowed past Earth constantly, day and night, year after year, regardless of what the sun was doing. Parker had discovered something fundamental about how stars actually work. Yet even after his vindication, one question remained. Where exactly did the solar wind come from? How did it accelerate? Why did it leave the sun at such tremendous speeds when the sun's gravity should have been pulling it back? For 60 years, no one could answer those questions because no one could go close enough to find out. The corona, the outer atmosphere of the sun, is bizarre in ways that defy intuition. The surface of the sun, which we call the photosphere, glows at roughly 10,000 degrees Fahrenheit. That's the visible disk you see in the sky. But the corona, the wispy crown of plasma extending millions of miles above that surface, burns at 1 to 3 million degrees Fahrenheit. The atmosphere of the sun is hundreds of times hotter than the surface of the sun. This violates everything we know about thermodynamics. When you stand near a fire, the farther you walk away from it, the cooler the air gets. The sun does the opposite. Move away from the surface, and the temperature explodes upward. Scientists called this the coronal heating problem, and it stood as one of the greatest unsolved mysteries in modern astrophysics. There were theories. Some scientists believed magnetic waves were carrying energy upward and depositing it in the corona. Others argued that tiny magnetic explosions, called nanoflares, were constantly heating the plasma from below. Still, others proposed that turbulence in the magnetic field was somehow accelerating particles to enormous temperatures. Every theory had supporters. Every theory had problems. And every theory was untestable because no spacecraft had ever been able to enter the corona and measure what was actually happening there. That changed on August 12, 2018, at 3:31 in the morning Eastern Time, when a Delta IV heavy rocket lifted off from Cape Canaveral carrying a spacecraft named after the very physicist who had been mocked 60 years earlier. Eugene Parker, then 91 years old, watched the launch in person. It was the first time NASA had ever named a spacecraft after a living person. The mission carried his name not just out of respect, but because every measurement it would make, every discovery it would return, would be a continuation of the work he started in 1958. The Parker Solar Probe was about to test the theories he had helped create against the brutal reality of the Sun's atmosphere. What scientists were about to learn would surprise everyone, including Parker himself. Within months of beginning its close approaches, the spacecraft would detect phenomena no model had predicted. It would discover that the solar wind near the Sun behaves nothing like the smooth, steady stream observed near Earth. It would find evidence of structures and processes that fundamentally changed our understanding of how stars produce wind, how coronal heating works, and how magnetic energy is converted into the radiation and particles that fill our solar system. And it would do all of this while enduring conditions that should have destroyed it. Temperatures hot enough to melt steel. Radiation environments more intense than anything any spacecraft had ever flown through. Speeds so extreme that the smallest miscalculation would have sent it tumbling into the Sun itself. The engineering required to make Parker's solar probe possible took decades of development and required materials and techniques that didn't even exist when Eugene Parker first proposed the solar wind. It required a heat shield made from a substance so specialized that only a handful of laboratories on Earth could produce it. It required orbital mechanics so complex that the spacecraft would use 7 separate flybys of Venus over 7 years just to bend its trajectory close enough to the Sun. And it required scientists and engineers willing to spend their entire careers on a mission whose first scientific results wouldn't arrive until years after launch. By 2026, Parker Solar Probe has completed 23 close approaches to the Sun. It has flown closer than any human-made object in history. It has sampled the corona directly multiple times in regions never before reached, and the data it has sent back has forced a complete rewrite of our understanding of how the Sun actually works. But before we dive into those discoveries, we need to understand exactly what scientists believed they knew before Parker arrived. We need to understand the picture of the Sun that had been built carefully over a century of telescopic observations and remote measurements, the picture that Parker was about to dismantle piece by piece. The idea of sending a spacecraft to the Sun is older than NASA itself. In 1958, the same year Eugene Parker published his controversial paper on the solar wind, a committee of American scientists assembled to plan the future of space exploration. They drew up a list of priority missions, and near the top of that list, ranked alongside lunar landings and Mars probes, was a single haunting goal: send a spacecraft to the Sun. They called it a solar probe mission. They imagined it would happen within a few decades. Instead, it would take 60 years. The problem was material science. In 1958, no substance existed that could survive close passage to the Sun. The aluminum and titanium alloys used in early spacecraft would soften and warp at temperatures the corona routinely reached. The electronics of the era could barely function in Earth orbit, much less in an environment where solar radiation would fry transistors in microseconds. Engineers knew what the mission required in principle. They just had no way to build it. The probe would need a heat shield, unlike anything ever constructed, a thermal protection system that could face temperatures of thousands of degrees on one side while keeping delicate instruments at room temperature only inches away on the other side. For decades, the mission lived only on paper. NASA studied it repeatedly through the 1970s, 1980s, and 1990s. Each study reached the same conclusion. The science was extraordinary. The engineering was impossible. The mission designs kept growing larger and more expensive as scientists tried to compensate for the limitations of available materials. By the mid-1990s, one proposed version called Solar Probe Plus was estimated to cost over $2 billion and would require a nuclear power source to handle the energy demands. Congress balked. The mission was repeatedly delayed, redesigned, scaled back, and shelved. The breakthrough came in 2007 when engineers at the Johns Hopkins Applied Physics Laboratory in Maryland began working on a completely new approach. Instead of trying to power the spacecraft through the heat with nuclear generators, they would use solar panels. But those solar panels would have to retract and hide behind the heat shield as the spacecraft approached the sun. Instead of a massive, multi-billion-dollar probe, they would build something smaller, lighter, and more focused. The mission would launch on a single rocket and use repeated gravity assists from Venus to gradually drop closer and closer to the sun over a period of years. Each pass would be slightly closer than the last, allowing the spacecraft to incrementally test its survival before committing to the deepest plunges. The redesigned mission was approved by NASA in 2009 under the name Solar Probe Plus, and full development began. The total cost would be around $1.5 billion, expensive but feasible. The launch date was set for 2018. That gave engineers less than a decade to solve problems that had stumped them for 60 years. The biggest of those problems was the heat shield itself. It would need to face direct sunlight, roughly 475 times more intense than what Earth receives. The front of the shield would reach temperatures of 2,500 degrees Fahrenheit, hot enough to melt aluminum, hot enough to cause many metals to glow red. And it had to keep the spacecraft body behind it at around 85 degrees Fahrenheit, roughly the temperature of a comfortable spring day. The solution was a sandwich structure. The front face would be made of carbon-carbon composite, a material developed for spacecraft heat shields and rocket nozzles, capable of withstanding extreme temperatures without losing structural integrity. Behind that face would be a layer of carbon foam, just 4.5 inches thick. Carbon foam is roughly 97% empty space, providing extraordinary thermal insulation in a very lightweight package. Behind the foam would be a second sheet of carbon-carbon composite, and the entire assembly would be coated with a specially developed white ceramic paint that would reflect as much sunlight as possible. The finished heat shield weighed only 160 pounds and was just 8 feet across, but it would be the most thermally extreme piece of hardware ever flown. To test it, engineers built specialized facilities. They constructed a custom solar simulator at NASA's Goddard Space Flight Center, a machine that could focus intense light onto small areas of the shield to verify it would behave as predicted. They subjected prototype materials to plasma torches, to vacuum chambers heated to extreme temperatures, to combined thermal and radiation environments designed to mimic what the spacecraft would face. Every test pushed the materials to their limits. Some samples failed. Engineers learned from each failure and refined the design. By 2017, the heat shield was complete and certified for flight. In 2017, NASA made an unusual announcement. They were renaming the mission. It would no longer be called Solar Probe Plus. It would be called the Parker Solar Probe, in honor of Eugene Parker, the physicist whose 1958 paper had predicted the solar wind. This was the first time NASA had ever named a spacecraft after a living person. Parker, then 90 years old, was reportedly stunned. He had spent his career fighting for ideas that were initially rejected. He had been mocked by his peers and nearly had his career destroyed by hostile reviewers. Now, 6 decades later, a billion-dollar spacecraft would carry his name into the atmosphere of the sun to directly measure phenomena he had predicted long before any technology existed to verify them. The launch was scheduled for late July 2018, but multiple delays pushed it into August. The rocket required was extraordinary. To reach the sun, you cannot simply point a spacecraft at it and fire the engines. Earth is moving around the sun at about 67,000 miles per hour. Any spacecraft launched from Earth inherits that velocity. To fall toward the sun, you have to cancel out most of that orbital speed, which requires enormous amounts of energy. The Parker Solar Probe needed to lose 53,000 miles per hour of orbital velocity to begin its journey inward. That required the Delta IV Heavy, one of the most powerful rockets in the American fleet, augmented with a third stage normally used for sending probes out of the solar system entirely. Counterintuitively, reaching the sun requires almost as much energy as escaping the solar system. The launch finally came at 3:31 in the morning on August 12, 2018. Eugene Parker watched from a viewing area at Cape Canaveral. The rocket lifted off through the pre-dawn darkness, its engines casting an orange glow that made the launch pad visible for miles. Within minutes, the spacecraft separated from the upper stage and began its long, looping trajectory toward Venus. The first Venus flyby would happen 6 weeks later, on October 3, 2018, bending the spacecraft's path inward toward the Sun. From there, the probe would make 6 more Venus encounters over the next 6 years, each one peeling away more of its orbital velocity, each one allowing it to dive closer to the star at the center of our solar system. By December 2018, just 4 months after launch, Parker Solar Probe had already broken records. It became the fastest human-made object ever, surpassing the previous record set by the Helios 2 probe in the 1970s. It became the closest human-made object to the Sun, also surpassing Helios 2, and it had not yet made even its first close approach. The real mission, the real discoveries, were still to come. But before those discoveries could rewrite our understanding of the Sun, scientists had to confront the picture of solar physics they had built over a century of observations from afar, because what they thought they knew was about to be tested. By the time Parker Solar Probe launched, solar physics had accumulated a century of careful observation. Telescopes on Earth, orbiting observatories like SOHO and SDO, ground-based coronagraphs in Hawaii and the Canary Islands, and earlier spacecraft like Helios, Ulysses, and Stereo, had built up an enormous body of data about the Sun. Scientists had constructed what they considered a coherent picture of how the star worked, from its blazing visible surface to the vast plasma bubble extending billions of miles into space. That picture was sophisticated. It was supported by equations, by simulations, by decades of measurement. And on the most important questions, it was wrong. The conventional understanding of the solar wind divided it neatly into 2 populations. There was the fast solar wind, traveling at roughly 500 to 800 kilometers per second, which scientists believed originated from regions on the Sun called coronal holes. Coronal holes are areas where the Sun's magnetic field opens up into space rather than looping back onto itself. They appear dark in ultraviolet images because they're cooler and less dense than surrounding regions. The standard theory held that magnetic field lines in coronal holes acted like superhighways, allowing charged particles to escape directly outward into space at high speeds. Then there was the slow solar wind, moving at 300 to 500 kilometers per second, which was thought to come from the boundaries of closed magnetic field regions called streamers, where field lines arched out from the Sun and then back down to the surface. The slow wind supposedly leaked out from the edges of these streamers in a kind of magnetic spillover. This 2-population model had been the foundation of solar wind physics for decades. It appeared in every textbook. It guided spacecraft mission designs. It informed predictions of space weather at Earth. Scientists were confident they understood the broad outlines, even if details remained fuzzy. Once the wind left the corona, they believed, it accelerated to a final speed within a few solar radii, and then traveled outward in a smooth, steady flow, gradually expanding into the larger heliosphere. The Parker spiral, named after Eugene Parker himself, described how the Sun's rotation would twist the magnetic field carried by this outflowing wind into a vast curving pattern that wrapped through the solar system like the streams of water from a rotating lawn sprinkler. The coronal heating problem, while officially unsolved, had narrowed to 2 leading explanations. The first was wave heating. Acoustic and magnetic waves generated by the violent convection beneath the Sun's surface would propagate upward, eventually depositing their energy in the corona and heating the plasma to millions of degrees. Specific types of magnetic waves, called Ulfvén waves after the Swedish physicist Hans Ulfvén, were considered the most likely candidates. These waves travel along magnetic field lines like vibrations along a guitar string, and they can carry energy across vast distances without losing it easily. The wave heating model predicted that the corona should be filled with detectable oscillations, with energy flowing steadily from below into the upper atmosphere. The second explanation was nanoflare heating, proposed by the astrophysicist Eugene Parker himself in 1988. According to this theory, the corona was heated not by smooth wave deposition, but by countless tiny magnetic explosions, each one releasing a small burst of energy as twisted magnetic field lines reconnected and snapped into simpler configurations. Individually, these nanoflares would be far too small and too brief to observe directly, but their combined effect over the entire surface of the Sun would be enough to maintain coronal temperatures of millions of degrees. The nanoflare model predicted that the corona should be in a state of constant low-level turbulence, with bursts of energy appearing and disappearing on time scales of seconds or shorter. For decades, scientists had debated which mechanism dominated. Observations seemed to support both, depending on which region of the corona was studied and which instruments were used. Some researchers proposed that both mechanisms operated simultaneously, with different processes dominating in different conditions. Without direct measurements inside the corona itself, the debate could not be resolved. Every remote observation could be interpreted through either lens. The magnetic environment of the inner heliosphere was thought to be well understood. The Parker spiral provided the basic geometry. The Sun rotated once every 25 days at its equator, dragging the embedded magnetic field around with it. As the solar wind flowed outward, it carried frozen-in magnetic field lines, which the rotation would gradually wind into spirals. Closer to the Sun, before the wind had fully accelerated, and before the rotation had significantly twisted the field, the magnetic lines should point nearly radially outward, like spokes on a wheel. This was a clean, predictable picture, grounded in straightforward physics. Models of space weather, predictions of geomagnetic storms at Earth, calculations of particle acceleration in solar events, all of them depended on this basic geometric framework being correct. The dust environment near the Sun was another active area of speculation. Astronomers had long known about the F-corona, a faint glow surrounding the Sun caused by sunlight scattering off interplanetary dust particles. This dust was thought to come from comets and asteroids gradually grinding themselves down over millions of years, spiraling slowly inward toward the Sun due to a process called Poynting-Robertson drag. The question was what happened to that dust as it got close enough to the Sun. Physics predicted that radiation pressure and sublimation should eventually destroy dust grains entirely. Below some critical distance from the Sun, the heat should be so intense that no solid material could survive. Calculations placed this dust-free zone somewhere between 4 and 5 million miles from the Sun's surface, but no observation had ever directly confirmed it existed. Some astronomers argued the zone must be there. Others suggested that new dust was constantly being delivered to replace what was destroyed, and that no true empty region would ever form. The debate had been going on since the 1920s. Energetic particle physics added another layer of confident assumption. Scientists believed they understood how the Sun accelerated charged particles to high energies during solar flares and coronal mass ejections. Shock waves driven by these explosive events would compress and accelerate ions and electrons to speeds approaching the speed of light. These particles would then stream outward through the heliosphere, occasionally bombarding Earth with radiation storms that could threaten astronauts and damage satellite electronics. The processes were thought to be well characterized, with established theories explaining the energy spectra and timing of observed events. Remote spacecraft had measured these particles after they traveled out to Earth orbit, and the data seemed to fit existing models reasonably well. The picture was complete. The Sun was a magnetized rotating star with a turbulent surface, a mysteriously overheated corona, two distinct populations of solar wind, a spiraling magnetic field, an outer atmosphere likely cleared of dust within a certain critical distance, and well-understood mechanisms for accelerating particles during energetic events. Solar physics had reached a kind of stable maturity. The remaining problems were considered details to be filled in, not foundations to be overturned. Then Parker Solar Probe made its first close approach in November 2018, and the very first batch of data revealed something so strange that the team initially thought their instruments were malfunctioning. Within months, it would become clear that the textbook picture of the Sun was not just incomplete. In several crucial respects, it was wrong. The first close approach happened on November 5 and 6 of 2018, just 3 months after launch. Parker Solar Probe came within 15 million miles of the Sun's surface, already closer than any spacecraft in history. The Helios 2 probe, which had held the previous record since 1976, had reached 27 million miles. Parker had nearly halved that distance on its very first perihelion. For about 11 days, the spacecraft was inside what mission planners called the encounter phase, with its instruments fully active, gathering data continuously, recording everything that happened in this unexplored region of space. But scientists on Earth could not see the data in real time. The spacecraft was on the wrong side of the Sun. Radio communication was impossible because the Sun itself blocked the signal path. The probe was on its own, alone, capturing measurements no one could verify or examine, storing them on solid-state recorders for later transmission. The mission team had to wait. They knew the spacecraft was inside the inner heliosphere, gathering data they had spent decades preparing to receive. They had to wait days, then weeks, for Parker to swing back into a position where the deep space network antennas could lock onto its signal and begin the slow process of downloading what it had recorded. The first telemetry packets arrived in early December. They confirmed the spacecraft was healthy. All systems had survived the encounter. The heat shield had performed perfectly. Temperatures behind it had stayed within expected ranges. Power systems were nominal. The instruments had operated continuously throughout perihelion. Engineers exhaled. The hardware had worked. Now the scientific teams could begin examining what those instruments had recorded. The data trickled down slowly. Parker Solar Probe's transmitter was relatively low power, and at the distances involved, downloading a complete data set from a single encounter could take weeks. Different instrument teams received their data in batches. The field's team, which managed the magnetic field and electric field measurements, was among the first to start serious analysis. Stuart Bale, the lead investigator for FILDS at the University of California, Berkeley, began examining the magnetic field traces. What he saw did not match anything he had expected. The magnetic field in the inner heliosphere, according to every model, should have pointed nearly radially outward from the Sun. Small variations were expected, of course. The field was not perfectly uniform, and turbulence would introduce some fluctuations, but the basic direction should have been stable. Instead, Bale saw the magnetic field repeatedly flipping. The direction would point outward, then within seconds it would suddenly reverse, pointing nearly backward toward the Sun, then it would flip again, returning to its outward orientation. These reversals were not gradual. They were sharp, almost violent transitions that lasted anywhere from a few seconds to several minutes before the field snapped back. At first, the team suspected an instrument problem. Sensitive electronics in the harsh environment near the Sun could behave unpredictably. Perhaps the magnetometers were experiencing some kind of glitch caused by thermal stress or radiation effects. They double-checked the calibration data. They examined the engineering telemetry. They compared readings from different instruments to see if the reversals showed up consistently across the spacecraft's sensor suite. Everything checked out. The instruments were working normally. The reversals were real. The magnetic field near the Sun was behaving in a way no observation had ever recorded and no theory had ever predicted. The reversals were not random either. They had structure. They came in groups, with bursts of activity followed by quieter periods. Some of them appeared to be associated with sudden increases in solar wind speed, as if whatever caused the magnetic field to flip was also accelerating the surrounding plasma. The team began calling them switchbacks, a casual term that would stick and eventually appear in dozens of scientific papers. No one yet understood what the switchbacks meant, but it was immediately clear that they represented something fundamental that previous theories had missed entirely. While the FILDS team puzzled over the magnetic data, the SWEAP team, responsible for measuring the solar wind directly, was finding its own surprises. Justin Casper at the University of Michigan led that team, and his group was examining the velocity and direction of the charged particles streaming past the spacecraft. The solar wind near the Sun should have been flowing primarily outward. away from the sun's surface. That part was correct. What was unexpected was a strong tangential component to the flow. The plasma was not just moving outward, it was also moving sideways, around the sun, in the same direction as the sun's rotation, with velocities far higher than any model had predicted. Models said the tangential flow should be small near the sun, growing only gradually as the spacecraft moved away from the source region. Instead, Parker was measuring tangential velocities of tens of kilometers per second, sometimes approaching values comparable to the outward flow itself. This meant either that the sun was transferring far more angular momentum to its escaping wind than anyone had calculated, or that the wind was originating in regions of the corona that nobody had identified as significant sources. Either possibility had major implications. The sun's rotation rate is slowly decreasing over geological time as it loses angular momentum to the solar wind. If the loss rate was higher than current models said, the long-term evolution of the sun would need to be reconsidered. The plasma density measurements added another layer of confusion. The density was higher than predicted in some regions and lower in others, with structures that did not fit cleanly into the established two-population model of fast and slow solar wind. There were plasma streams that should have been classified as slow wind based on their velocity, but had compositional signatures more typical of fast wind. There were other streams that mixed properties in ways the standard model could not accommodate. The simple categories that had organized solar wind physics for decades were breaking down on contact with direct measurements. The team met repeatedly through December and January, comparing notes across instrument groups. The mood was a mixture of excitement and bewilderment. Every dataset showed phenomena that did not fit existing models. The agreement between independent measurements made it clear the data was real, not an artifact of any single instrument. But what the data meant remained an open question. Eugene Parker himself, watching from his office at the University of Chicago, told reporters that he was thrilled and confused in equal measure. The mission named after him was returning results that surprised even him. By the time the second perihelion approached in April 2019, the team had begun to grasp the scale of what they were dealing with. The first encounter had not been a fluke, it had been a preview. The switchbacks, the unexpected tangential flow, the breakdown of the standard wind categories, all of it pointed to a sun that was fundamentally more dynamic, more complex, and more poorly understood than anyone had realized. The conventional picture of solar physics was not just incomplete in minor details. It was missing entire phenomena that played central roles in how the sun interacted with the rest of the solar system, and the spacecraft was about to go even closer. To understand how Parker Solar Probe accomplished what it did, you have to understand the spacecraft itself. Not just the heat shield, but everything behind it. Every system on board had to be reimagined for an environment no spacecraft had ever operated in. The result was a machine unlike anything NASA had built before, packed with engineering solutions that pushed materials science, electronics, and orbital mechanics to their limits. The spacecraft body sits directly behind the heat shield, a compact cylindrical assembly about the size of a small car, weighing roughly 1,500 pounds at launch. The hexagonal bus contains the avionics, the propellant tanks, the communication electronics, and the scientific instruments. The entire body has to remain in the heat shield's shadow at all times during close approach. If any portion of the spacecraft slips out of that shadow, even briefly, it would face the full intensity of unfiltered sunlight and could be permanently damaged within seconds. Maintaining perfect orientation is not just a matter of good navigation. It is a survival requirement. To handle this, the spacecraft uses an autonomous attitude control system that constantly monitors its position relative to the sun. Small solar limb sensors are positioned along the edge of the heat shield. If sunlight begins to spill onto these sensors, they trigger an immediate response. The spacecraft fires its thrusters or repositions itself within milliseconds to restore the protective shadow. This system has to operate completely independently. During the closest approaches, Parker is on the far side of the sun from Earth, with all radio communication blocked. There is no possibility of mission controllers stepping in to correct a problem. The spacecraft must defend itself. Power comes from solar arrays, which presents a paradox. The closer the spacecraft gets to the sun, the more intense the sunlight, and the more electricity solar panels can generate. But that same intensity would destroy any normal solar array within minutes. Standard panels would overheat catastrophically. The voltage they produced would spike beyond what the electronics could safely handle. Engineers solved this with a retractable solar array system. As Parker approaches the sun, the panels gradually fold inward, hiding behind the heat shield. Only narrow strips of the panels remain exposed to direct sunlight at the closest approaches. This strip-shaped configuration limits power generation but prevents thermal disaster. Even this limited exposure produces enormous heat in the panels themselves. To keep them from melting, the array is cooled by a custom water-based liquid cooling system. Roughly 2 gallons of deionized water circulate through tubes embedded in the panel structure, carrying heat away from the cells to radiators positioned in the spacecraft's shadow where they can dump the energy into space. The system is a closed loop. The water never escapes. Pumps move it continuously through the panels and radiators throughout every perihelion. The cooling system is one of the most thermally stressed components on the spacecraft, operating reliably for years in conditions where any leak or failure would end the mission immediately. Behind the heat shield sit 4 primary instrument suites, each designed to answer specific scientific questions. Fields measures electric and magnetic fields, with antennas and sensors mounted on booms that extend out from the spacecraft body. Some of these antennas actually project beyond the edge of the heat shield, becoming the only parts of the entire spacecraft exposed to direct sunlight during perihelion. They are made of niobium, a refractory metal that can survive temperatures over 2,000 degrees Fahrenheit without losing structural integrity. Even so, they glow red hot during close passes, while still measuring electromagnetic phenomena with extreme precision. SWEAP, the solar wind electrons, alphas, and protons investigation, characterizes the particles streaming past the spacecraft. Its most exposed component is the solar probe cup, a Faraday cup mounted on the side of the spacecraft, positioned to look directly at the sun. This single instrument is engineered to do something almost no other piece of hardware on Parker is permitted to do. It stares straight into the unfiltered sun. The cup is built from materials that can survive the resulting temperatures, including specialized tungsten-rhenium alloys for the most exposed surfaces and sapphire crystal insulators for the electronics. When this cup is at its closest approaches, parts of it reach temperatures over 1,800 degrees Fahrenheit. The fact that an instrument can operate at such temperatures and still produce useful scientific data was considered nearly impossible by many physicists before the mission flew. Letter 298 is the integrated science investigation of the sun, measures energetic particles, the high-energy ions and electrons that are accelerated by solar flares, coronal mass ejections, and the various shock waves that propagate through the inner heliosphere. The instrument package includes 2 complementary sensors, one optimized for lower energy particles and one for higher energy events. Together, they characterize particles from a few thousand electron volts up to hundreds of millions of electron volts, capturing the full spectrum of the sun's energetic output. WISPR, the Wide Field Imager for Solar Probe, is the only camera on board. It does not photograph the sun directly. That would be impossible at these distances and would risk damaging the sensor. Instead, WISPR looks sideways, photographing the corona and solar wind structures from inside them. The result is an entirely new perspective on the sun's outer atmosphere. Where previous spacecraft had photographed the corona from far outside, looking inward, WISPR captures images from within the corona itself, looking outward and to the side. This vantage point reveals streamers, blobs of plasma, and shock waves as they sweep past, often crossing through the spacecraft's actual position. It is the first time anyone has ever seen the corona this way. The communication system uses a high-gain antenna that has to be carefully managed during encounters. Most of the time, the antenna cannot point at Earth, because doing so would require the spacecraft to rotate in ways that would expose vulnerable surfaces to direct sunlight. Instead, the spacecraft stores all its data internally during the encounter phase, then transmits it back to Earth during the quieter portions of its orbit, when it is far enough from the Sun to safely reorient. The data downloads happen over weeks. The Deep Space Network's 3 large antenna complexes in California, Spain, and Australia receive the signals. A typical encounter can generate tens of gigabytes of scientific data, all of which must be transmitted through a narrow communication window using a relatively modest transmitter. The orbital design uses Venus to do the heavy lifting. Each time Parker swings past Venus, the planet's gravity bends the spacecraft's trajectory, lowering the closest approach distance to the Sun by a few million miles. 7 Venus flybys are planned over the course of the mission, each one tightening the orbit. The 7th and final Venus encounter, scheduled for November 2024, would set up perihelions where the spacecraft passes within 3.83 million miles of the Sun's surface. At that distance, Parker would be inside the corona itself, deep within the Sun's atmosphere, traveling at over 430,000 miles per hour, fast enough to cross the continental United States in about 20 seconds. Every component of this spacecraft represents a compromise between competing demands. Mass had to be minimized to fit on the rocket. Power had to be managed against thermal constraints. Instruments had to balance sensitivity against survival. The result is a machine that is small, lightweight, and extraordinarily specialized, designed for one purpose only: to survive close passes to the Sun and return data from a region of space that humans had only theorized about for centuries. Now, with the spacecraft proven and the instruments returning data, the discoveries were about to come in earnest. And the first major revelation, the one that would dominate the early years of the mission, was already taking shape in those mysterious switchbacks. By November 2019, exactly 1 year after the first close approach, 4 papers appeared simultaneously in the journal Nature. They represented the first comprehensive scientific results from Parker Solar Probe, and they marked the formal public introduction of switchbacks to the wider scientific community. The papers were treated as an event in solar physics. News outlets covered them. Conference sessions were organized around them. Theorists who had spent careers modeling the inner heliosphere suddenly had to reckon with a phenomenon they had never anticipated. The mission had been operating for barely a year, and it had already produced a result that would shape the field for the next decade. What the data revealed was both simple and bewildering. The magnetic field in the inner solar wind did not flow smoothly outward from the Sun in the orderly Parker spiral that every textbook described. Instead, it was filled with violent S-shaped kinks, regions where the field line would bend so dramatically that it doubled back on itself, pointing momentarily inward toward the Sun before snapping back to its outward direction. These were the switchbacks. They were not minor fluctuations. They were full reversals, sometimes lasting several minutes, during which the magnetic field would point in completely the wrong direction. The structures came in clusters. A region of relatively calm field would be punctuated by storms of switchbacks, dozens or hundreds occurring within a few hours, followed by another quiet period. The clusters appeared to be tied to specific source regions on the Sun. Whenever the spacecraft was magnetically connected to certain areas of the corona, the switchbacks intensified. When the connection mapped to other regions, the field became smoother and more predictable. This pattern suggested the switchbacks were being generated at or near the Sun's surface, not produced by some process happening in interplanetary space. Even more striking was the velocity signature. Inside each switchback, the plasma moved faster than the surrounding wind. The kink in the magnetic field was accompanied by a jet of accelerated material, as if something at the Sun was periodically firing pulses of plasma outward. These accelerated jets carried the kinked field with them as they traveled, propagating outward at high speeds. Over time, as the wind moved away from the Sun, the switchbacks gradually relaxed and dissipated, which explained why spacecraft farther out, like the older Helios probes or the various satellites near Earth's orbit, had never observed them in this dramatic form. By the time the switchbacks reached those distances, they had smoothed out into the gentler fluctuations that had been recorded but never recognized as the remnants of a much more violent inner heliospheric phenomenon. The immediate question was what could possibly produce such structures. Theorists offered competing explanations within weeks of the first papers appearing. One leading idea involved a process called interchange reconnection, in which open magnetic field lines from a coronal hole reconnect with the closed loops of a nearby magnetic region. When two field lines of opposite orientation meet, they can snap together and rearrange themselves into a new configuration. The energy released by this rearrangement would launch a pulse of plasma outward, dragging the kinked field along with it. According to this picture, switchbacks would be the signatures of countless small magnetic explosions happening in the lower corona, each one releasing a tiny burst of energy and material into the solar wind. A second explanation focused on turbulence. Some researchers argued that the switchbacks were not generated at the sun at all, but instead developed naturally as Alfvén waves propagated through the solar wind. Under certain conditions, these waves could grow in amplitude until they steepened into nonlinear structures that resembled the observed switchbacks. This model had the advantage of explaining why the structures relaxed over distance. As they traveled outward, energy would gradually leak away into smaller scales, smoothing the kinks back into ordinary wave-like fluctuations. A third proposal suggested that switchbacks came from the granulation pattern visible on the sun's surface. The sun's photosphere is covered with millions of convection cells, each about the size of Texas, constantly bubbling up from below, releasing energy and sinking back down. The boundaries between these cells, where the hot rising plasma meets the cooler descending material, are sites of intense magnetic activity. Footpoints of magnetic field lines, anchored in these boundaries, get jostled around by the convection, and each jostle could send a perturbation propagating up the field line into the corona and beyond. Over time, these perturbations could accumulate and steepen into the switchbacks Parker was observing. For several years, the competing models all had supporters. The data alone could not distinguish between them definitively. The switchbacks had complex statistical properties, and each theory could explain some features of those properties while struggling with others. As Parker made more close approaches and gathered more data, the picture gradually clarified. By 2023, multiple independent studies had converged on a hybrid view. The switchbacks appeared to be generated primarily by interchange reconnection in the lower corona, with their detailed properties shaped by the dynamics of the convection patterns at their footpoints. The turbulence model captured some aspects of how they evolved during their outward journey, but their origin was clearly anchored in specific physical events near the sun. The implications went beyond just explaining a curious magnetic phenomenon. Switchbacks turned out to carry a significant fraction of the energy and momentum of the solar wind itself. They were not a side effect. They were a major component of how the wind was launched. This meant that the standard picture of solar wind acceleration, in which the wind built up speed smoothly as it moved outward through the corona, was incomplete. A substantial portion of the acceleration was happening in discrete bursts, packaged into structures that arrived as a series of magnetic and plasma pulses rather than a continuous stream. This had consequences for understanding how the sun loses mass and angular momentum over time. The total mass loss rate was not changed, but the mechanism for that loss looked different. The sun was not slowly breathing out a continuous wind. It was sputtering, exhaling in countless small bursts that combined at large distances into what appeared from afar to be a steady stream. The angular momentum carried away by these bursts could be significantly different from what smooth flow models had calculated, with implications for the long-term spin-down of the sun and other stars like it. For the scientific community, the switchback discovery served as a warning. If a phenomenon this prominent and energetically important had remained completely undetected for 60 years of solar wind research, what else might be hidden in the regions of space too close to the sun to observe from a distance? The two-population model of fast and slow wind, the clean Parker spiral, the gradual smooth acceleration, All of these had been built on observations made far from the source. The closer Parker got to the actual launching regions of the wind, the more its picture diverged from what models had said it would find. And the switchbacks were just the beginning. The mission was about to descend further into the corona itself, and what waited there would call into question even more fundamental assumptions about how stars work. On April 28, 2021, something happened that no spacecraft had ever done before. Parker Solar Probe crossed an invisible boundary in the Sun's atmosphere, and for the first time in history, a human-made object was inside a star. NASA did not announce the achievement immediately. The data took months to download and analyze. It was not until December 2021, more than 7 months after the actual event, that the agency confirmed what had taken place. The spacecraft had crossed the Ulfvén critical surface, a boundary that solar physicists had theorized about for decades, but had never been able to directly observe. To understand why this mattered, you have to understand what the Ulfvén critical surface actually is. The Sun's corona is filled with plasma threaded by magnetic field lines, and waves can propagate through this plasma along those field lines. These are called Ulfvén waves, named after the same Swedish physicist mentioned earlier as a candidate for heating the corona. The waves travel at a specific speed determined by the strength of the magnetic field and the density of the plasma. Close to the Sun, the magnetic field is intense and the Ulfvén wave speed is very high. Far from the Sun, the field weakens and the wave speed drops. The solar wind, meanwhile, is constantly accelerating as it moves outward. Near the Sun's surface, it moves slowly. Farther out, it speeds up. At some critical distance, the wind velocity matches and then exceeds the local Ulfvén wave speed. That crossing point is the Ulfvén critical surface. Below it, any disturbance traveling on the magnetic field lines can race back down to the Sun faster than the wind itself can carry material outward. The plasma remains in causal contact with the Sun. It is, in a real physical sense, still part of the solar atmosphere. Above the surface, the wind moves too fast for any signal to travel back. Disturbances can only propagate outward. The plasma has truly left. It belongs to the heliosphere now, not to the Sun. For all of solar physics history, this boundary had been an abstract concept. Models placed it somewhere between 10 and 20 solar radii, roughly 4 to 9 million miles from the Sun's surface. But these were estimates based on remote observations and theoretical calculations. No instrument had ever been close enough to measure the actual location. Crossing it would mean entering the corona itself, the region where the Sun's atmosphere ends and interplanetary space begins. It would mean becoming, for a few hours at a time, a part of the Sun. Parker's 8th perihelion took place over several days in April 2021, with the spacecraft reaching its closest approach at about 8.4 million miles from the Sun's surface. The FILDS instrument detected the moment of crossing. The character of the magnetic field changed. The relationship between magnetic and plasma pressure shifted in a specific way that indicated the spacecraft had moved from a region where the wind was supralfvenic to one where it was subalfvenic. The plasma surrounding Parker was no longer escaping the Sun. It was still part of the Sun. The crossing lasted about 5 hours before the spacecraft moved back out into the wind that had escaped the boundary. What was completely unexpected was the shape of the surface itself. Theoretical models had pictured the Ulfvén critical surface as a smooth, roughly spherical shell surrounding the Sun. The reality was something else entirely. The surface had spikes and dips. It was wrinkled and irregular, with extensions that reached far out into space and indentations that dropped deep toward the Sun. As Parker traveled along its orbital path, it passed through this irregular boundary multiple times, dipping in and out of the corona as the warped surface rose and fell around it. The spacecraft did not cross once and stay inside. It crossed, then exited, then crossed again, sometimes within just a few minutes. The wrinkles were not random. They corresponded to specific structures on the Sun's surface. Where Parker passed, near a region called a pseudostreamer, a tall structure of magnetic field that extended high into the corona, the Ulfvén surface bulged outward dramatically. The pseudostreamer was pushing the boundary out further than its surroundings, allowing the spacecraft to enter the corona at distances where, in other directions, the wind would already have been fully escaping. Other features on the Sun produced corresponding dips in the surface. The geometry of the boundary was directly tied to the magnetic landscape below it. This finding had significant implications. The standard picture had assumed the corona ended at roughly the same height all around the Sun, give or take some smooth variations. Instead, the corona had a complex three-dimensional structure with features extending much farther in some directions than others. This meant that solar wind streams emerging from different regions of the Sun spent dramatically different amounts of time within the corona before fully escaping. Streams from regions where the Alfvén surface extended high would remain in causal contact with the Sun for longer distances, allowing more interaction between the wind and the solar atmosphere. Streams from regions where the surface dipped low would escape almost immediately. This had consequences for how the wind acquired its properties. The composition, temperature, and turbulence characteristics of solar wind streams are partly determined by the processes that act on them during their time in the corona. Wind streams that lingered longer would experience more heating, more turbulence, more compositional adjustment. Wind streams that escaped quickly would carry the properties of their source regions out into space relatively unchanged. The wrinkled surface explained, at least partially, why different solar wind streams have such diverse properties despite all originating from the same star. The crossings also confirmed something important about coronal heating. Inside the Alfvén surface, the magnetic field was dominated by structures and waves that carried significant energy. Outside it, those same energy reservoirs were largely absent. The transition was sharp. This suggested that whatever process was heating the corona to millions of degrees was strongly associated with the subalfvénic regime, with the conditions that prevailed below the critical boundary. The findings did not definitively resolve the wave heating versus nanoflare heating debate, but they did localize where the action was happening. The heating occurred predominantly inside the Alfvén surface, in the region where Parker was now able to make direct measurements for the first time. Subsequent perihelions returned the spacecraft to the boundary repeatedly. Each crossing added more data, refined the picture, and gradually mapped the warped geometry of the surface in greater detail. By the time the mission had completed a dozen passes through the Alfvén surface region, scientists had built a three-dimensional model of how the boundary behaved, how it responded to changes in solar activity, and how it connected to specific features visible on the Sun's disk. The crossing was a milestone for the mission and for solar physics as a whole. A spacecraft had entered a star's atmosphere and survived to return data. The corona was no longer an inaccessible region observed only at a distance. It had become a place where measurements could be made directly. And those measurements were already beginning to reveal that the corona, like the wind that escaped from it, contained structures and processes that nobody had anticipated, including, as the next discovery would show, something the spacecraft was never designed to find. Among the strangest things Parker's solar probe was about to find was something that was not there. For nearly a century, astronomers had argued about whether a region of empty space surrounded the Sun, a zone so close to the star that no solid material could survive. The idea dated back to the late 1920s, when researchers studying the faint glow around the Sun realized that interplanetary dust particles, sliding gradually inward over millions of years, must eventually reach temperatures hot enough to vaporize them entirely. There had to be a boundary, a critical distance inside of which all dust simply evaporated. Below that line would lie a dust-free zone, a true emptiness encircling the star. The theory was elegant. The evidence was thin. Telescopes on Earth and in orbit could observe the F-corona, the dust-scattered glow extending outward from the Sun, but they could not actually see the inner cutoff. The intensity of direct sunlight near the Sun was so overwhelming that any potential dust depletion zone was buried beneath the glare. For decades, astronomers debated whether the zone really existed, where its boundary lay, and how sharp the transition would be. Some argued for a clean cutoff. Others suggested a gradual fade. A few even questioned whether the zone existed at all, proposing instead that new dust was continuously delivered by infalling comets and asteroids, maintaining a dense population all the way down to the solar surface itself. Parker's solar probe had not been designed primarily to settle this debate. The WISPR imager, the spacecraft's only camera, had been built to photograph coronal structures and solar wind features. But the same instrument could also measure dust by recording how much sunlight was being scattered toward it from particles along its line of sight. As Parker moved closer to the Sun than any previous mission, WISPR would naturally collect data on the dust environment in regions no instrument had ever seen. The first hints emerged during the early perihelions. As the spacecraft approached the Sun, the brightness of the F corona in WISPR images did not increase as rapidly as a uniform dust distribution would predict. Something was changing in the dust population. Russell Howard and his colleagues, who led the WISPR team, examined the data carefully. They mapped how the dust-scattered brightness varied with distance from the Sun. By the time Parker reached about 19 solar radii, the dust density was clearly starting to decrease. By 15 solar radii, the depletion was unmistakable. Closer still, the dust thinned out further, eventually approaching a level so low that it became hard to distinguish from the other sources of background light in the images. The dust-free zone existed, or more precisely, a dust depletion zone existed, with the steepest drop-off occurring at about 7 solar radii, around 3 million miles from the Sun's surface. The depletion was not absolutely complete. Some residual dust remained even at the closest distances Parker measured, kept there by a constant trickle of new material delivered from the outer solar system. But the density inside the depletion zone was reduced by a factor of several compared to what a smooth, undepleted distribution would have predicted. The decades-old hypothesis was confirmed with measurements that finally gave the boundary a real location and a real shape. But while WISPR was finding less dust than expected in the inner regions, the FILDS instrument was finding something else. It was detecting dust impacts on the spacecraft itself. Parker was traveling at speeds exceeding 400,000 miles per hour during its closest approaches. At those velocities, even a tiny dust grain, far smaller than a grain of sand, hits the spacecraft with enormous kinetic energy. The impact vaporizes a small amount of the spacecraft's surface material, producing a tiny burst of plasma. That plasma generates a brief electromagnetic pulse, which the FILDS antennas detect as a sharp spike in the electric field signal. Parker was getting hit constantly. During each perihelion, the spacecraft recorded thousands of dust impacts. Most were too small to cause any meaningful damage. But each one was vaporizing a microscopic piece of the heat shield, or the antennas, or the bus structure. Engineers had anticipated this. The spacecraft had been designed to absorb a certain amount of dust erosion without compromising its function. Even so, watching the impact data accumulate over the course of multiple encounters, it became clear that the dust environment was more hostile than some models had suggested. The impacts themselves provided scientific information. The rate and energy distribution of impacts allowed researchers to map the dust population in detail, revealing structures that WISPR alone could not see. There were regions of higher dust density that appeared to be associated with the orbital paths of specific known asteroids and comets, suggesting that those bodies were leaving trails of debris that drifted inward and eventually intersected Parker's orbit. There were variations with solar activity, as if the wind itself was sweeping dust around or pushing it into new configurations. The dust environment was dynamic, not static, just as the wind and the magnetic field had turned out to be. One particularly striking observation involved a kind of cometary effect. As Parker swept through the dust population at hypersonic speeds, the impacts themselves generated material that streamed away behind the spacecraft. Each impact released a small cloud of vaporized debris that lingered briefly before dispersing. WISPR captured images of this trailing material. From a distance, Parker's solar probe looked, for a moment, like a tiny comet, leaving a faint glowing wake as it raced through the inner heliosphere. The wake was created by the spacecraft itself. by the cumulative effect of countless dust impacts releasing material from its own surface and from the dust grains it was colliding with. The pattern that had been forming through earlier discoveries was becoming clearer. The standard picture of the inner heliosphere had treated it as a relatively passive environment shaped by a few smooth processes. Parker was finding the opposite. The wind was punctuated by switchbacks. The corona had a wrinkled boundary that extended different distances in different directions. The dust population was structured by external delivery from comets and asteroids and modified by impacts and erosion. Everywhere the spacecraft looked, it found dynamic, irregular phenomena that earlier generations of solar physicists had either missed or treated as minor perturbations on top of an essentially clean baseline. The closer to the sun the spacecraft got, the less the textbook descriptions resembled what was actually there. The corona was not a smooth medium with a few interesting structures. It was a complex three-dimensional environment full of jets and pulses and boundaries that wrinkled and shifted in response to processes happening on the sun's surface and in its interior. The wind did not flow smoothly outward. It bursted and switched and accelerated in jets. The dust did not fill a uniform population. It thinned out in some places and gathered into trails in others, modified by the spacecraft's own passage. Everything was more textured, more dynamic, more variable than anyone had expected. And the next discovery would extend this pattern to one of the most basic categories solar physicists had been using for decades: the distinction between fast and slow solar wind. The foundational classification that organized everything from space weather predictions to stellar evolution models was about to come apart. For 60 years, solar wind physics had been organized around a simple distinction. The fast solar wind, moving at speeds above roughly 500 kilometers per second, came from coronal holes. The slow solar wind, moving below that threshold, came from the boundaries of helmet streamers and other closed-field regions. This classification was not just a convenience. It reflected real differences in the composition, temperature, and behavior of the two populations. Fast wind was hotter in certain ways, lower in heavy element abundance, and carried characteristic plasma signatures that distinguished it from slow wind. The two streams behaved like different fluids with different origins and different histories. Parker's solar probe was supposed to clarify the boundary between these two populations by sampling each one closer to its source. Instead, the spacecraft began returning data that blurred the distinction beyond recognition. Wind streams that should have been clearly classified as one type instead exhibited properties that mixed features of both. Even more puzzling, some streams appeared to be slow wind based on velocity, but carried the chemical fingerprints of fast wind. Others moved at fast wind speeds, but had elemental compositions that matched the closed-field source regions of slow wind. The chemical fingerprints are key to understanding what was happening. Different regions of the corona process elements in different ways. In open field regions, where magnetic lines lead directly to interplanetary space, charged particles can escape quickly without spending much time in the hot corona. In closed field regions, where magnetic lines arch back down to the sun, particles are trapped for longer and undergo more thermal processing. This processing affects the relative abundances of different elements, particularly heavier ones like iron and silicon, in a way that depends on how long the plasma resided in the corona before escaping. Measuring those abundances in the solar wind effectively tells you where it came from. The composition is a fossil record of the wind's origin. Parker's measurements showed that some slow wind streams had compositional signatures characteristic of open-field source regions. According to the standard model, this should have been impossible. Slow wind from streamer boundaries should carry the closed-field signature, having spent significant time in the trapped corona before being released. Yet here was wind moving slowly, but bearing the chemical evidence of a fast wind origin. Either the standard model of where slow wind comes from was wrong, or some process was modifying the wind's velocity after it left a fast wind source region. The puzzle deepened as more data accumulated. Statistical studies of multiple perihelions revealed that the situation was not a few anomalous cases, but a widespread pattern. A significant fraction of slow solar wind, perhaps as much as half during certain epochs, appeared to come from open field regions despite its low speed. The reverse was also true. Some fast wind streams carried composition signatures that suggested closed field origins. The two populations were not as separate as decades of remote observations had implied. They overlapped, mixed, and exchanged properties in ways the standard model could not accommodate. A new picture began to emerge, built around a process called interchange reconnection. Already implicated as a possible source for switchbacks, interchange reconnection was now appearing as a far more pervasive phenomenon than anyone had recognized. The basic idea is that open and closed magnetic field lines do not stay segregated. At the boundaries between coronal holes and the surrounding closed field regions, the two field topologies are constantly meeting and rearranging. When an open field line and a closed loop come into contact under the right conditions, they can swap partners. The open line connects with one footpoint of the loop, while the other footpoint of the loop becomes the new open line. The result is that material previously trapped inside the closed loop suddenly finds itself on an open field line, free to flow out into the solar wind. This process turns out to happen everywhere in the corona, not just at the large boundaries of coronal holes. Small ephemeral coronal holes appear and disappear constantly on the sun's surface. Tiny magnetic loops emerge from the solar interior, interact with surrounding fields, and disappear again. Each of these events provides opportunities for interchange reconnection to release small bursts of trapped plasma into the open field circulation. Over the entire surface of the Sun, this happens continuously, with thousands of small reconnection events occurring every day. The S-Web model, originally proposed in the 2010s before Parker launched, gained dramatic new support from these findings. The model proposes that the corona is laced with a network of narrow corridors where open and closed field lines meet and continuously reconnect. These corridors form a complex web of S-shaped patterns across the Sun's surface, hence the name. The S-web acts as a pathway through which closed field plasma can escape into the open field circulation, mixing the two populations together. According to the model, slow solar wind from boundary regions is not really coming from a distinct source. It is escaping from closed field regions through these reconnection corridors, picking up its slow velocity and its closed field composition in the process. Parker's data fit this picture better than the older model. The mixed populations the spacecraft was observing were exactly what the S-Web predicted. The patchy, variable nature of the wind, with rapid transitions between different stream types over short distances, made more sense if reconnection was happening continuously across the entire corona rather than only at the large boundaries between coronal holes and streamers. The switchbacks themselves could be understood as visible signatures of individual reconnection events that had released bursts of trapped plasma into the open field circulation. The implications reached well beyond solar wind classification. If interchange reconnection was the dominant mechanism for releasing slow solar wind, then a significant fraction of the Sun's mass loss was happening through these tiny magnetic explosions rather than through smooth outflow from coronal holes. This affected estimates of how much material the Sun loses over time, how much angular momentum it sheds, and how rapidly it spins down. Similar mechanisms operating on other stars would have similar effects on their evolution. The discovery also bore on the coronal heating problem. Each reconnection event releases magnetic energy, some of which goes into accelerating the released plasma and some of which heats the surrounding gas. If reconnection was happening continuously across the corona, it provided a natural heating mechanism that operated everywhere, all the time. This was essentially Eugene Parker's nanoflare idea, but with a specific physical realization. The countless small magnetic explosions that Parker had proposed in 1988 to heat the corona were now being identified, decades later, as the interchange reconnection events that Parker Solar Probe was detecting through their wind signatures. There were still details to work out. Not all of the reconnection events Parker observed could be cleanly linked to specific source regions on the Sun. The exact contribution of interchange reconnection to total mass loss remained uncertain, with estimates ranging widely depending on assumptions. Other mechanisms, including the wave-driven heating processes that competed with the nanoflare model, almost certainly still played roles alongside reconnection. The picture emerging was not a clean replacement of old theories with a new one. It was a more complex synthesis in which multiple processes operated together, with their relative importance varying across different regions of the corona and different conditions. What was clear was that the simple two-population model of fast and slow wind no longer served as an accurate description of reality. The wind was a continuum, not a binary. And the closer Parker got to the sun, the more the categories that solar physicists had spent decades defining and refining started to dissolve into something more interesting and more difficult to summarize. The next finding would push that complexity even further. Because among everything Parker measured during its closest approaches, one observation stood out as more disorienting than the others. It would force scientists to confront not just the limits of their models, but the limits of their basic intuitions about what was even possible inside the atmosphere of a star. The most shocking discovery did not come as a single observation. It came as a synthesis, a moment when the disconnected pieces from years of measurements suddenly clicked together into a single picture that nobody had seen coming. By 2023 and into 2024, the data from multiple perihelions had accumulated enough that researchers could compare what Parker measured in space with what other spacecraft were observing on the sun's surface at the same moments. The Solar Orbiter mission, launched by the European Space Agency in 2020, was returning high-resolution images of the corona from a different vantage point. NASA's Solar Dynamics Observatory had been watching the sun continuously since 2010. When scientists overlaid the datasets, they saw something extraordinary. Every time Parker detected a burst of switchbacks or a sudden acceleration in the solar wind, they could trace the magnetic connection back to a specific point on the sun and find, at that exact location and exact moment, a tiny eruption. Not a major flare, not a coronal mass ejection, something much smaller, almost invisible against the brightness of the corona, lasting only minutes. These small eruptions were called coronal jets, and astronomers had been observing them for years without understanding their significance. The new measurements revealed they were not occasional curiosities. They were everywhere. Thousands of them were happening across the sun every day, and each one was a small launching event for the solar wind. The picture that emerged was startling. The sun does not produce wind by smoothly breathing plasma outward through coronal holes. The sun produces wind by firing it. The wind we measure near Earth is not a continuous flow. It is the smoothed-out, averaged-down remnant of countless individual jets, each one launching a packet of plasma and magnetic energy outward through the corona. By the time these packets reach Earth's orbit, they have merged and dispersed enough to look like a single stream. Up close, near the launching points, the structure is still visible. The jets are still distinct. The switchbacks Parker had been recording were the magnetic signatures of those individual jets traveling outward through the wind they had themselves created. What was even more striking was the size scale. Many of these jets were tiny. Some were called jetlets, ranging from a few hundred to a few thousand kilometers across, lasting only 1 or 2 minutes. Individually, they would have seemed too small to matter on the scale of an entire star. But their combined effect added up to something enormous. The total energy released by all these small eruptions across the sun's surface was comparable to or greater than the energy needed to heat the corona and accelerate the solar wind. The mystery that had stood for nearly a century, the question of what was heating the corona and what was launching the wind, had been answered by phenomena that were almost too small to see. This was Eugene Parker's nanoflare idea, vindicated again, but in a more concrete and detailed form than he had originally proposed. In 1988, Parker had suggested that countless tiny magnetic explosions could heat the corona. He could not have known how literally correct that proposal would turn out to be. The jets that Parker's solar probe was now connecting to its in situ measurements were exactly the kind of small magnetic explosions Parker had envisioned, occurring at the rate and with the cumulative power he had estimated. The man whose career had been mocked in 1958 for proposing the solar wind, and whose 1988 paper on nanoflare heating had been treated as speculative, was now seeing both of his radical ideas confirmed by a spacecraft bearing his name. The implications reframed essentially everything about how the sun interacts with the rest of the solar system. Solar wind streams were not coherent rivers flowing from defined source regions. They were the aggregate of vast numbers of small individual launches, each one a discrete event with its own properties. The two-population model of fast and slow wind dissolved because both populations were really collections of individual jets, with the apparent differences emerging from where and how those jets occurred. The coronal heating problem dissolved because the heating was being delivered by the same jets that were producing the wind. The picture of the sun as a star with a stable, smoothly flowing atmosphere gave way to a picture of the sun as a star whose atmosphere is in constant, violent, small-scale upheaval everywhere on its surface. The new picture had consequences that went beyond solar physics. Other stars, presumably, work the same way. The winds blown off other stars, the heating of their coronas, the angular momentum they lose over time, would all be governed by similar small-scale processes. This affected models of stellar evolution, which depended on accurate mass loss rates. It affected models of how planetary atmospheres erode under stellar wind pressure, which depended on the structure and energy of the wind. It affected interpretations of remote astronomical observations of other stars, where the unresolved jets would average together into the apparent steady winds that telescopes recorded from a distance. For habitability questions, the new picture changed the conversation. Planets around other stars were not bathed in smooth stellar winds. They were being hit by streams of individual plasma packets, each one carrying its own embedded magnetic field, each one a small space weather event. Earth's magnetic field deflects most of these arrivals, but worlds without magnetic protection, like Mars, were being weathered by countless small impacts rather than by uniform pressure. The slow erosion of Mars's atmosphere over billions of years, which had transformed it from a potentially habitable world into a desiccated wasteland, was being accomplished by exactly this kind of granular bombardment. For the search for life elsewhere in the galaxy, the findings added urgency to questions about magnetic protection. Worlds orbiting active young stars would be bombarded much more heavily than Earth is today. Whether life could establish itself, and whether it could persist long enough to develop complexity, depended in part on how individual planetary atmospheres responded to the particulate granularity of stellar wind. The smooth wind models had underestimated the violence of the interaction. The new models, built on what Parker had found, had to incorporate the fact that the wind hits in pulses. There were elements of the picture that remained unresolved. The exact mechanisms by which the small jets generate switchbacks were still being worked out. The relative contributions of different types of magnetic events to total heating and wind launching were still being measured. The way the jets connect to deeper processes in the sun's interior, where the magnetic fields originate before erupting through the surface, was not yet clear, but the basic outline was secure enough that textbooks were being rewritten. Solar physics had a new foundation, built on direct measurements inside the corona itself, and the foundation looked nothing like the smoothly flowing picture that had organized the field for half a century. Eugene Parker did not live to see the full synthesis. He died in March 2022 at the age of 94, several years after his namesake spacecraft had begun returning the data that would confirm his theories more thoroughly than anyone could have predicted. He had seen the early results, including the switchback discoveries, before he passed. He knew the mission was succeeding beyond expectations. The full vindication of his career came posthumously in papers published over the years that followed, demonstrating that the radical ideas he had defended against his peers were even more correct than he had dared to claim. And the mission was not done. Parker still had years of perihelions ahead. The deepest passes, the closest approaches, were still to come. What Parker Solar Probe has accomplished is not just a series of individual discoveries. It is a structural change in how an entire scientific field organizes its understanding of stars. Textbook chapters have been rewritten. University courses have updated their core material. Doctoral dissertations that were being written based on the old framework have been redirected mid-research. The pre-Parker picture of the Sun, which had served solar physics for 50 years, has not been entirely discarded, but it has been deeply reformed, with new foundations and new emphases that students learning the subject today encounter as the established consensus. The most prominent casualty is the smooth wind paradigm. Models that assumed the solar wind was a continuous flow with broad-scale variations are now treated as a coarse approximation valid only at large distances from the Sun. The granular, pulse-driven nature of the inner heliosphere has been incorporated into next-generation models that explicitly include discrete launching events. These models are computationally expensive, requiring the simulation of countless small jets and their evolution as they propagate outward, but they reproduce the observed properties of the wind far better than the older smooth flow versions did. Researchers who built their careers on smooth wind simulations have had to retool their codes or partner with theorists who can implement the new framework. The coronal heating problem, which had been a defining open question of solar physics for nearly a century, has effectively been resolved, or at least narrowed to a degree where remaining disagreements concern details rather than fundamentals. The energy needed to maintain coronal temperatures comes from the same magnetic reconnection events that launch the wind. This single answer covers both questions that have been treated as separate puzzles. The heating and the wind acceleration are aspects of the same underlying process, not independent phenomena requiring different solutions. Decades of papers debating wave heating versus nanoflare heating now read as a long approach to a synthesis that direct measurements finally made possible. The Parker spiral itself, the geometric pattern named after Eugene Parker that describes how the Sun's rotation twists the heliospheric magnetic field, has not been overturned. It remains correct as a large-scale average, but the detailed structure of the field, with its switchbacks and its rapid local reversals, departs dramatically from the smooth spiral in the inner heliosphere. The spiral is now understood as an emergent pattern that becomes visible only after averaging over the many smaller structures that fill the wind. At small scales, the field is highly disordered. At large scales, the order reasserts itself. Both descriptions are valid, but the field is no longer pictured as smoothly conforming to the spiral at all scales. Models of stellar mass loss have been updated with consequences that extend far beyond the Sun. Every star like our Sun loses material through a wind driven by the same underlying processes. The rate at which a star sheds mass affects its long-term evolution, its eventual lifespan on the main sequence, and the conditions it produces for any planets in orbit around it. Older models that calculated mass loss based on smooth wind assumptions underestimated certain components and overestimated others. The new models, calibrated against Parker's measurements at the Sun and extrapolated to other stars based on their properties, are producing revised estimates of stellar mass loss across a wide range of stellar types. These revisions ripple into models of star clusters, of galactic chemical evolution, and of the gradual enrichment of interstellar gas with heavier elements ejected by stellar winds over cosmic time. Angular momentum loss is a related issue that has been similarly affected. As a star sheds its wind, the wind carries away some of the star's rotational momentum. Over billions of years, this process causes stars to spin down. The rate of spin down depends on the geometry and dynamics of the wind. Smooth wind models had produced one set of predictions for how quickly stars slow their rotation. The new pulse-driven models produce different numbers, with implications for stellar age estimates based on rotation rate. A technique called gyrochronology, which uses rotation period as a proxy for age, has had to be re-examined in light of the new findings. Some calibrations have shifted. Some stellar ages have been revised. The relationship between solar interior dynamics and the heliosphere has been forced into the spotlight. The small jets that launch the wind are connected to magnetic activity that originates beneath the sun's visible surface, in the convection zone where heat is transporting by the bubbling motion of plasma. Understanding how the deep interior produces the surface magnetic features that then erupt as jets has become a higher priority for solar physics. The interior is harder to observe directly than the corona, but indirect techniques like heliosismology, which uses sound waves traveling through the sun to map its internal structure, have become more important. The interior and the corona, once treated as relatively independent domains, are now studied as a coupled system in which processes at depth determine processes at the surface and beyond. Space weather forecasting has been transformed by the new picture. Predictions of when geomagnetic storms will hit Earth, how severe they will be, and what their effects on satellites and power grids might be, all depend on models of how solar wind structures propagate from the sun to Earth. The discovery that the wind is fundamentally granular at its source has forced forecasters to upgrade their tools. Old models that propagated smooth wind streams have been replaced by ones that incorporate discrete launching events and track them as they evolve. The new models are still imperfect, and accurate space weather prediction remains an active research challenge, but the foundation is sounder. The disconnects between predictions and observations that had frustrated forecasters for years are gradually being reduced as the models incorporate the realities Parker has revealed. Comparative studies of other stars have benefited from the new framework. Telescopic observations of stellar coronas, made with X-ray and ultraviolet instruments, can now be interpreted within a model that treats the activity as a collection of small jets and reconnection events rather than as a smoothly heated medium. Young, active stars produce far more jets than our middle-aged sun does, which explains their brighter coronas, their stronger winds, and their more violent space weather. Old stars produce fewer jets and have correspondingly quieter atmospheres. The full life cycle of a star, from its energetic youth to its quiet old age, can be understood as a gradual decline in the rate of these small magnetic events. For exoplanet research, the implications are practical and immediate. Models of how stellar winds shape and erode planetary atmospheres have to account for the pulsed nature of the wind. Models of how host stars affect the climate and habitability of orbiting planets have to incorporate the granular structure of the radiation and particle environment those planets experience. The interpretation of biosignatures, of atmospheric markers that might indicate life, depends on understanding how the host star modifies the atmosphere through its wind. The pre-Parker models had used smooth wind assumptions that underestimated certain interactions. The new models produce different predictions, sometimes by significant margins, about which exoplanets might retain atmospheres and which would have them stripped away by their host stars over geological time. In a real sense, what Parker has done is not just discover new things about the sun. It has given astronomy a more accurate picture of how all stars work, and through that picture, a more accurate framework for asking questions about every planetary system in the galaxy. The discoveries Parker Solar Probe has made are not abstract. They touch the daily lives of every person reading this. The granular, pulsed nature of the solar wind that Parker revealed has direct consequences for the technology our civilization depends on, and improving our understanding of that wind directly improves our ability to protect the infrastructure that keeps modern society running. Consider what happens during a major solar storm. In February 2022, just a few years after Parker began returning its first results, a coronal mass ejection struck Earth's magnetic field. The event was not particularly large by historical standards. It was the kind of moderate storm that happens many times during each 11-year solar cycle, but its timing was unfortunate. SpaceX had just launched 49 new Starlink satellites into low Earth orbit. The storm heated Earth's upper atmosphere, causing it to expand outward. This expansion increased the atmospheric drag on the newly launched satellites, which were still in the lowest part of their orbits before being raised to their operational altitudes. 38 of the 49 satellites failed to reach their planned positions and re-entered the atmosphere, burning up over the Caribbean. The economic loss was estimated at over $50 million. The cause was a routine solar event whose effects on the upper atmosphere had been underestimated by the operational space weather forecasts. This kind of loss is becoming more common as low Earth orbit becomes more crowded. SpaceX alone operates thousands of Starlink satellites. Competing constellations from other companies add thousands more. Government and military satellites occupy still more orbital slots. All of these spacecraft are vulnerable to atmospheric drag effects driven by solar activity. Every improvement in space weather forecasting reduces the risk of mass deorbits during storms. Parker Solar Probe's measurements have fed directly into improved drag models, allowing satellite operators to plan launches and altitude adjustments with better information about what the sun is likely to do. The risk extends to satellites at higher altitudes as well. Geostationary communications, satellites, weather satellites, and GPS satellites all operate in regions of space that can be disturbed by solar activity. Geomagnetic storms can charge spacecraft electronics, induce currents that damage components, and degrade solar panels through cumulative radiation exposure. The GPS signal that guides cars, airplanes, ships, and increasingly important agricultural and industrial systems depends on satellites that are vulnerable to space weather. During severe storms, GPS accuracy can degrade significantly, affecting everything from navigation in remote areas to precision agriculture to military operations. Aviation is another area where Parker's discoveries have practical consequences. Polar flights, which cross over Earth's magnetic poles where the planet's protective field is weakest, are particularly exposed to solar particle events. Pilots and passengers on these flights receive higher radiation doses than they would on equatorial routes. During major solar storms, airlines often reroute polar flights to lower latitudes, adding hours and significant fuel costs to long-haul journeys between North America, Europe, and Asia. Better forecasting of solar particle events means fewer unnecessary reroutes and better protection during actual events. The improved understanding of how the sun launches energetic particles, which Parker's measurements have contributed to, helps make those forecasts more accurate. Then there is the power grid. Electricity transmission lines act as enormous antennas that pick up the geomagnetically induced currents created during solar storms. These currents can overload transformers, damage electrical equipment, and in extreme cases trigger cascading blackouts that affect millions of people. In March 1989, a major geomagnetic storm knocked out the Hydro-Quebec power grid in Canada, leaving over 6 million people without electricity for 9 hours. The economic damage was estimated in the hundreds of millions of dollars. More recent assessments suggest that a sufficiently severe storm could cause cascading failures across continental power grids, with damages potentially reaching trillions of dollars and recovery times measured in months to years. The historical event that haunts space weather researchers is the Carrington event of 1859. That storm, the largest in recorded history, induced currents so strong that telegraph systems caught fire, sparks flew from operator keys, and auroras were visible as far south as the Caribbean and Hawaii. The storm occurred when humanity had almost no electrical infrastructure to damage. If a Carrington-class event happened today, the consequences would be catastrophic. Estimates of damage range from $1 to $2 trillion, with recovery times that could exceed a decade for the most severely affected grids. Parker Solar Probe's measurements feed into better understanding of how the most extreme solar events develop and propagate, which in turn improves our ability to anticipate and mitigate them. For the future of space exploration, Parker's findings are especially important. Plans to return humans to the Moon and eventually send crews to Mars depend on understanding the radiation environment astronauts will face during their journeys. A solar particle event during a deep space mission could deliver lethal doses of radiation to crew members unprotected by Earth's magnetic field. Forecasting such events accurately and providing astronauts with enough warning to take shelter in radiation-protected sections of their spacecraft requires understanding how the sun produces and accelerates the particles in question. Parker has provided some of the most detailed measurements ever made of how energetic particles are generated and how they propagate outward through the inner heliosphere. Mission planners for crewed deep space exploration are using this data to design spacecraft, plan trajectories, and develop operational procedures that will keep astronauts safe. The current solar cycle, which peaked around 2024 and 2025, has been more active than forecasters initially predicted. Auroras have been visible at unusually low latitudes, including across much of the United States and Europe, in events that have surprised the public and given many people their first sight of the northern or southern lights. These auroral displays are beautiful, but they are also reminders of the energetic environment surrounding our planet. The same storms that produce auroras also induce currents in pipelines, disrupt high-frequency radio communications, and stress electronic systems. The greater frequency of significant events during this cycle has provided extensive data for testing the new space weather models that incorporate Parker's findings. Beyond practical infrastructure protection, the cosmic ray connection to climate remains an active research question. Over geological timescales, the rate at which cosmic rays from the broader galaxy penetrate the heliosphere and reach Earth's atmosphere has varied significantly. These variations are partly driven by changes in the sun's activity, with quieter periods allowing more cosmic rays to reach Earth and more active periods deflecting them away. Cosmic rays affect atmospheric chemistry, contribute to cloud nucleation, and influence the carbon-14 record that scientists use to date archaeological samples and reconstruct past climate. Parker's measurements of how the heliosphere shields the inner solar system from galactic cosmic rays help refine the models that connect solar activity to Earth's atmospheric history. For ordinary people, the most direct connection is the simple fact that the technology of daily life is more reliable than it would otherwise be. Power flows, GPS works, airplanes fly polar routes safely, satellites stay where they belong, the internet keeps functioning. None of these things happens automatically. They happen because engineers, forecasters, and scientists work continuously to anticipate and counter the effects of a star that is more dynamic than we used to realize. Parker Solar Probe has given those workers a more accurate picture of what the sun actually does, which means better protection for the systems everyone depends on. Despite everything Parker Solar Probe has accomplished, the sun remains a star full of unsolved problems. The mission has answered certain questions while exposing many others. Some of the new puzzles arose because Parker found phenomena that were not anticipated, and explaining them has opened new lines of inquiry that did not exist before the mission flew. Other questions are ones solar physicists have been asking for decades, which Parker has approached but not fully resolved. The next generation of missions and theoretical work is being organized around these remaining mysteries. The dynamo problem stands as one of the largest unfinished questions. The sun's magnetic field is generated deep in its interior by the motion of conducting plasma in a region called the tachocline, where the rotation rate of the outer convection zone meets the more uniformly rotating radiative zone beneath. The shearing motion between these layers, combined with the chaotic flows in the convection zone above, produces the magnetic field that emerges through the surface and drives the activity Parker has been measuring. The basic physics is understood in broad outline, but the details remain frustratingly unclear. Why does the sun follow an 11-year activity cycle? Why is each cycle slightly different from the previous one? Why do some cycles produce extreme grand minima like the Maunder minimum of the 17th century, when sunspots virtually disappeared for decades? Parker cannot answer these questions directly because they involve processes deep inside the sun, far below the surface and corona where the spacecraft operates. Solving them requires advances in heliosismology and in theoretical modeling that are proceeding in parallel with Parker's work. The initiation of coronal mass ejections is another open problem. These massive eruptions, which expel billions of tons of plasma into the heliosphere, are responsible for the most severe space weather events. Scientists understand the general processes that drive them, involving the buildup of magnetic energy in stressed configurations that eventually become unstable and release their energy explosively. But predicting when a specific magnetic region will erupt and how large the resulting ejection will be remains beyond current capability. Parker has flown through several coronal mass ejections during its mission, providing detailed measurements of their internal structure. These observations have refined the models, but the fundamental question of what triggers an eruption at a specific moment is still unresolved. Forecasters can identify regions of the Sun that are likely to produce eruptions, but they cannot reliably predict the exact timing. The European Space Agency's Solar Orbiter, which launched in 2020, has been operating alongside Parker since the early part of the decade. The two missions are complementary. Parker travels closer to the Sun and makes direct measurements of the corona and inner heliosphere. Solar Orbiter approaches less closely, but carries imaging instruments that can photograph the Sun at high resolution and a payload that includes spectrometers capable of measuring the composition of plasma in the corona. The combination of in situ measurements from Parker and remote imaging from Solar Orbiter has been one of the most productive partnerships in solar physics, with the two spacecraft regularly coordinating observations of the same magnetic structures from different vantage points. Solar Orbiter is also gradually tilting its orbital plane to look at the Sun from higher latitudes, eventually providing the first detailed views of the Sun's polar regions, which have never been imaged in high resolution from any spacecraft. NASA's Punch mission, the polarimeter to unify the corona and heliosphere, launched in March 2025. Punch consists of 4 small spacecraft that together image the corona and the inner heliosphere as a single connected system. The mission is designed to track solar wind structures from their origins near the Sun outward through the region where they would eventually reach Earth, providing continuous coverage that no single instrument has been able to achieve. Punch does not approach the Sun the way Parker does, but it provides the broader context in which Parker's localized measurements can be interpreted. Together with Parker and Solar Orbiter, Punch gives solar physicists a multi-perspective view of how the Sun produces and shapes its heliospheric environment. The MUSE mission, the multi-slit solar explorer, is being developed for launch later in the decade. MUSE is designed to take high-cadence spectroscopic observations of the corona, capturing the rapid changes that occur during small-scale reconnection events. The instrument can record dozens of slices of the corona simultaneously, allowing detailed mapping of how energy is released during the kind of jets Parker has connected to solar wind generation. The expectation is that MUSE will provide the most direct view yet of the actual events that launch wind packets, complementing Parker's measurements of what those packets look like once they have escaped into space. A more ambitious concept under study is the Helio Swarm mission, which would deploy a coordinated formation of 9 spacecraft to map the small-scale turbulence and reconnection that fill the inner heliosphere. Many of the processes Parker has observed are too small in extent to be characterized by a single spacecraft. Helio Swarm would essentially scale up the measurement strategy, with multiple spacecraft sampling different points in a turbulent region simultaneously to reveal 3-dimensional structure that no single probe can capture. The mission has been approved for development and is expected to launch in the early 2030s. Even more ambitiously, NASA and other space agencies have been studying an interstellar probe concept, a mission that would venture far beyond the heliopause to directly sample the local interstellar medium and the boundary of the Sun's influence. This mission would essentially extend the Voyager exploration into a planned, instrumented modern campaign, using a spacecraft designed specifically for the interstellar environment. The interstellar probe would not be ready for launch until at least the 2030s and would not return its most important data until decades later, but it represents the next logical step in the exploration of the heliospheric boundary. For the Sun's polar regions, the eventual goal is a dedicated polar orbiter that could observe the polar magnetic fields directly. The polar fields are critical to the dynamo because they reverse polarity at solar maximum and then reorganize during the descending phase of each cycle, setting the conditions for the next cycle. Current observations of the polar fields are limited because we view them from low angles, looking along the rotation axis rather than down onto the poles. A solar polar orbiter would provide the first clear view of how the polar magnetic field evolves through the cycle, with implications for cycle prediction and dynamo modeling. The mission has been studied for decades and remains on the long-term agenda of major space agencies. Other open questions concern the connection between the Sun's behavior and the broader galactic environment. The heliosphere itself moves through the local interstellar medium, and the conditions in that medium affect the shape and properties of the heliosphere's boundaries. As the Sun travels through different regions of the galaxy over millions of years, these conditions change. The heliosphere we measure today is a snapshot of its current state. Past and future heliospheric configurations would look different, with consequences for cosmic ray flux at Earth and possibly for terrestrial climate over geological time scales. Connecting Parker's measurements to longer-term variations in the local interstellar medium is a research direction that crosses between solar physics, planetary science, and galactic astronomy. The mission itself is approaching its operational endgame. Parker's seventh and final Venus flyby occurred in November 2024, locking the spacecraft into its closest possible orbit. The deepest perihelions, where Parker passes within 3.83 million miles of the Sun's surface, have been taking place since then, with the final pass scheduled for 2025. After that, with no more gravity assists available, the spacecraft will continue on its current orbit indefinitely. It will keep returning data until its instruments fail or its propellant runs out. The mission has years of operation ahead, but its deepest dives are nearly behind it. There is a moment worth pausing on, a moment that captures something essential about what has happened and what it means. On April 28, 2021, when Parker Solar Probe crossed the Ilfane critical surface for the first time, a human-made machine became, in a real physical sense, part of a star. The plasma surrounding it was no longer escaping into space. It belonged to the Sun. The boundary that had separated the atmosphere of our nearest star from everything else had been crossed by something we built. For a few hours, a piece of human engineering existed inside the Sun. Think about what that means in the context of our species' history. For nearly all of human existence, the Sun has been a presence in the sky that we could observe but never reach. Ancient civilizations across every continent worshipped it, told stories about it, organized their calendars around its motions. The Egyptians built temples aligned with its rising. The Mayans calculated its cycles with extraordinary precision. The Greeks gave it a name and assigned it to a god riding a chariot. Across thousands of years and hundreds of cultures, the Sun was a thing humans could see, depend on, fear and revere, but never approach. It was the ultimate untouchable. Galileo turned a telescope toward it in the early 1600s and saw spots moving across its surface. He realized the Sun rotated. He recognized that the spots were not flaws in his instrument, but real features on the Sun itself. The discovery cost him difficulties with the Catholic Church and contributed to ideas that would eventually reshape human understanding of our place in the cosmos. For centuries after Galileo, the Sun was studied through ever better telescopes, with ever more sensitive instruments, but always from the same fundamental position. We were on Earth. The Sun was up there. The distance between us was unbridgeable. It was not until the 20th century that we even came to understand what the Sun is. The realization that stars are powered by nuclear fusion, that they convert hydrogen into helium in their cores and release the energy that warms planets and drives life, did not become firmly established until the 1930s and 1940s. The picture of how a star works, of what processes generate its light, and its solar wind, and its magnetic field, was built up gradually through theoretical work by physicists like Hans Bethe and Eugene Parker, and many others. The understanding took form in mathematical equations and computational models, in laboratory experiments simulating stellar interiors, in increasingly sophisticated observations of distant stars. Eugene Parker, the man whose name the spacecraft now carries, contributed crucial pieces to that understanding. When he proposed the solar wind in 1958, he was not just predicting a phenomenon. He was changing how we conceived of the sun itself. Before Parker, the sun could be imagined as a glowing sphere with relatively stable boundaries, emitting light into space, but not actively flinging matter outward. After Parker, the sun became a star that constantly exhaled, that filled the space around it with plasma and magnetic field, that connected itself to its planets through a continuous flow of matter and energy. The boundary between the sun and the solar system became blurred. We were not orbiting near a star. We were orbiting inside its extended atmosphere. Parker's idea was a conceptual revolution that took decades to be fully appreciated. Even after the solar wind was confirmed by Mariner 2 in the early 1960s, the implications continued to unfold. The heliosphere as a whole, the vast bubble of solar wind that extends out beyond Pluto and into interstellar space, is essentially the sun's atmosphere expanded to fill the entire solar system. Every planet, every moon, every asteroid and comet, every particle of dust in the inner solar system exists within this atmosphere. We are not external to the sun, we are inside it. Parker Solar Probe took that picture and pushed it to its logical extreme. If we live inside the sun's extended atmosphere, then traveling to the sun is not really a question of distance. It is a question of depth. We are already in the outer layers. The mission was to descend into the deeper layers, into the corona, into the dense region where the wind is born. And when it crossed the Ulfvane critical surface, the spacecraft entered the deepest layer that any human-built object had ever reached. It became, for those hours, a piece of the sun, a piece of us inside a star. The achievement is staggering when you place it in the context of how long it took to get here. The first humans capable of looking up at the sun and wondering about it lived roughly 300,000 years ago. The first written records about the sun date back perhaps 5,000 years. The first scientific observations using instruments date back about 400 years. The first realization that the sun is a star like other stars came about 150 years ago. The first measurements of the solar wind happened about 65 years ago. The first time a spacecraft entered the sun's atmosphere happened in 2021. The entire history of recorded civilization fits between the early astronomical observations and the moment Parker crossed the Ulfvane surface. And the entire history of physical understanding of the sun fits between Galileo and the present day. We did this, a species that emerged on one small planet that for most of its existence had no concept of what stars actually are, built a machine that survived inside the atmosphere of its nearest star. The cumulative effort represents thousands of human lifetimes of work. Eugene Parker's contributions alone took place over more than 60 years of active research. The engineers who built the heat shield drew on materials science developed over a century. The orbital mechanicians who calculated the Venus flybys used mathematics refined over 4 centuries since Kepler. Every piece of the mission was built on accumulated knowledge passed down across generations. And the knowledge keeps growing. The data Parker is returning will be analyzed for decades. Scientists who were not yet born when the mission was conceived will spend their careers working through what it has revealed. Future missions will be designed based on what Parker has shown. The understanding of how stars work, of how they shape the planets around them, of how they influence the possibility of life across the galaxy, will continue to evolve. We are not finished learning about the sun. We are barely past the beginning. There is something profoundly hopeful about this. As a species, we are capable of looking at something seemingly impossible, an object whose surface is hot enough to vaporize anything we could build, and finding a way to reach it anyway. We are capable of carrying forward projects across generations, with people who will never meet contributing pieces to the same puzzle. We are capable of patience and persistence on time scales longer than any individual life. The Parker Solar Probe is not just a scientific instrument. It is a statement about what humans can do when they decide that understanding something matters more than how hard it is. In the long history of our species, We have done many things that were terrible. We have also done some things that were beautiful. Building a machine that could touch the sun belongs in the second category. It is the kind of achievement that, if any record of our civilization survives long enough to be discovered by some future intelligence, would deserve to be remembered. Tonight we explored what Parker Solar Probe found inside the sun. A spacecraft launched in 2018, named for a man whose ideas had once been ridiculed, traveled to a place no human-made object had ever been, and returned data that rewrote our understanding of the star that gives us life. The mission proved that the solar wind is not a smooth river, but a barrage of countless individual pulses. It showed that the corona is wrinkled and warped, not the smooth shell of textbooks. It confirmed that a dust-free zone surrounds the sun, settling a debate that had lasted a century. It demonstrated that the heating of the corona, the long-standing mystery that had stood for nearly 100 years, is accomplished by the same small magnetic explosions that launch the wind. It dissolved the clean two-population model of fast and slow solar wind into a continuous spectrum shaped by reconnection events scattered across the entire surface of the star. Each of these discoveries on its own would have justified the mission. Taken together, they amount to a transformation of solar physics. The picture of the sun that students learn today is fundamentally different from the picture that was taught a decade ago. Future textbooks will go further, incorporating findings that Parker is still returning, refining the framework as the data continues to come in. The mission has years of operations ahead. The deepest dives are happening now. Every perihelion adds more measurements, more details, more pieces to the evolving understanding. And yet, for all of that, the sun keeps its secrets. Parker has answered specific questions and exposed deeper mysteries underneath. We now understand how the wind is launched, but the magnetic dynamo that produces the surface activity remains poorly characterized. We have observed the Ulfvane critical surface and mapped its wrinkles, but the precise relationship between deep interior processes and surface emergence is still being worked out. We have direct evidence that small magnetic explosions heat the corona, but predicting when and where the next major eruption will occur is still beyond reach. The sun is more transparent to us than it was, but it remains a vast and dynamic object whose full behavior we have not yet fully captured. There is something fitting about this. The closer we get, the more we see. The more we see, the more we realize we do not yet understand. This is the pattern of scientific exploration generally. Every horizon once reached reveals further horizons beyond it. The Voyager spacecraft, traveling outward, found that the boundary of the solar system was more complex than anyone had predicted. The Parker Solar Probe, traveling inward, found that the sun itself is more complex than anyone had predicted. The two missions are mirror images of each other, both teaching the same fundamental lesson. Reality, when measured directly, always turns out to contain more than our models suggest. Right now, as you read or listen to this, sunlight is reaching you that left the surface of the sun about 8 minutes and 20 seconds ago. The photons carrying that light were generated in the sun's core when nuclear fusion converts hydrogen into helium. The photons took roughly 100,000 years to work their way from the core to the surface, scattering through dense plasma the entire way. They escaped through the photosphere into the corona, and from there into the heliosphere, racing outward at the speed of light until they reached Earth, where they warmed your skin or illuminated the screen you are looking at. The plasma those photons emerged through, the corona, is the same region Parker Solar Probe has been measuring directly. The wind those photons accompanied is the same wind whose granular nature Parker has revealed. The sun whose light keeps you alive is a star we are no longer entirely strangers to. The spacecraft itself will keep operating for years. Its current orbit, locked in after the seventh and final Venus flyby, will bring it back to its closest perihelion distances repeatedly. Each pass through the corona will return more data. Eventually, the propellant that Parker uses to keep its heat shield oriented correctly will run low. When that happens, the spacecraft will lose its ability to maintain perfect alignment. Without the protection of the shield, the spacecraft body will be exposed to direct sunlight during close approach, and it will be destroyed almost instantly. The mission will end with the spacecraft falling into the sun, becoming part of the star it was sent to study. It will be a fitting conclusion for a mission whose entire purpose was to reach into the atmosphere of a star. Parker Solar Probe will not drift forever like the Voyagers. It will return home to the sun and become part of the plasma it spent its operational life measuring. When it happens, sometime in the late 2020s or 2030s, the data archive will remain. Decades of scientists will continue mining it for insights. The names of the researchers who designed the instruments, who analyzed the data, who built the framework that emerged from the measurements, will be known to specialists. The general public will mostly forget the spacecraft, but the understanding it produced will persist. The way we think about stars, about our solar system, about the radiation environment we live in, will carry the imprint of what Parker Solar Probe accomplished. Long after the spacecraft itself has been vaporized in the corona, its measurements will continue to shape how humanity sees the universe. That permanence is what makes exploration worth doing. Not the spacecraft, which will eventually fall. Not the careers of the individual scientists, which will end. Not even the institutions that managed the mission, which will eventually be reorganized or replaced. The permanence is in the knowledge itself, which once acquired cannot be unlearned. Future civilizations on Earth, if they exist, will inherit what Parker has taught us. Future intelligences elsewhere in the galaxy, if any exist and ever encounter the legacy of human science, would find these results among the things we managed to discover before we faded. The sun's secrets, once revealed, are revealed for as long as anyone is curious enough to read about them. This is the spirit of exploration that runs through both the Voyager mission to the edge of the solar system and the Parker Solar Probe mission to its center. Two opposite journeys, made by the same species, driven by the same essential impulse, the desire to know what is out there, the willingness to commit decades of effort to answering questions that may not be settled within any individual lifetime, the trust that knowledge gained matters even when its applications are not yet visible. We are a species that builds machines to touch the sun and machines to leave the solar system. We have done both within a few decades of each other, with technology that started crude and became extraordinary, carried forward by people whose names most of us will never know. Whatever else is true about humanity, this is true. We look up at the sky and ask what is there. And sometimes, against all odds, we find a way to go look for ourselves. If you enjoyed exploring the secrets of our nearest star with us tonight, take a moment to like this video and subscribe to the channel. Comment below with what discovery surprised you the most, or what mystery about the sun you would most want to see solved next. Share this video with someone who would appreciate the story. Every like, every comment, every subscriber helps this channel keep bringing you deep journeys into the most extraordinary corners of our universe. Until next time, keep looking up. The cosmos is still full of stories waiting to be told.